Okay, so here we're going to do an example, and what we have is a sphere of homogeneous linear dielectric material, and it's placed in an otherwise uniform electric field. And what we must do is find the electric field inside the sphere. Now, the blue arrows indicate the direction of the electric field. It's in the direction of the z-axis. R is the radius of our sphere, and theta is the angle between the z-axis and our point of observation. So, since both inside and outside the sphere there are no free charges, what we must do here is solve Laplace's equation. And we're going to do this for the potential inside, and the potential inside is going to depend on R, and it's going to depend on theta. So that's for R less than or equal to big R. And we can also do it for outside, depends on R and theta. That's for R greater than or equal to the radius. Now we will solve Laplace's equation for the proper boundary conditions. So now what are those boundary conditions? Well, the first boundary condition that we have is that the potential must be continuous. Okay, and it must be continuous across the surface. So we have the potential in will equal the potential out, and that's at R is equal to the radius. Now the second boundary condition that we can have is the change in the electric field. So what we will have is, or the change in potential, so we'll have the permittivity. Now this is inside, so this is where I'm writing the permittivity as epsilon dV in divided by the n, and that's going to be equal to the electric field outside, or the change in the potential outside, which is dV out divided by the n. Now what you see here is, importantly, on the left hand side what we have is the permittivity, and on the outside we have the permittivity of free space. Okay. Now also this results because there are no free charges at the surface. Okay, so this is boundary condition number 2. Now our third boundary condition is what happens at infinity. So at infinity the potential outside is going to go to minus E0 or cos theta. Okay, and this is for R much greater than R. So why is it doing this? Well, at infinity the potential is that of a homogeneous electric field. So essentially the way that this could be written is the potential will be equal to minus E naught by Z, which is minus E naught or cos theta. Okay, so these are our 3 boundary conditions. Now, from separation of variables, the general solution to Laplace's equation can be found. And this is for a spherical coordinate system. Okay, so how this would look is we would have the potential, which depends on R and theta, and this would be equal to the sum from L is equal to 0 to infinity for AL or to the power of L plus BL divided by R to the L plus 1 by PL cos theta. Okay, now this is a general solution to Laplace's equation in spherical coordinates. We're not going to go through it in detail. It can be found in, for example, chapter 3 of Griffiths. But what I just want to draw your attention to is here at the end, and what we have is a Legendre polynomial in the variable cos theta. Okay, in the variable cos theta. And we're going to use this with the appropriate boundary conditions in order to solve for the constants which are given up here, which is RA and B.